All right, folks, here we are kicking off a new chapter, and in section 5.1, we're going to look at a topic called approximating area under a curve. Now, in calculus, there are two big questions. Big question number one, compute the slope of a tangent line, also known as the instantaneous rate of change. And we have seen that the derivative answered this question. Big question number two was area under a curve. So again, we've seen how to answer the first big question using derivatives. We now address the second big question, area under a curve. But before we do that, we need to review some notation that you may have seen in a previous mathematics class. And it's the notation we need to take a look at is the sigma notation. That's the Greek letter sigma. And its meaning in mathematics is to sum or add up. So let's look at an example. This is an example that I'm just going to do on the slide, not going to go off to the board. So in A, I would read that as the sum from I equals 1 to 5. The I equals 1 and the 5 are called the indices. I equals 1 tells us where we're starting, and the 5 tells us where we're ending. So it's the sum from I equals 1 to I. Now what that means – 1 plus 2 plus 3 plus 4 plus 5. Start at an I value of 1. Then you go to the next I value, which means you just increment by 1. The next I value would be 2, and so on. So part B, the sum I equals 1 to 5 of 2i, well, that will start at an I value of 1. So, you see 2i. That means the first number we see should be 2. Plus, then the next I value would be 2. So 2 times 2 is 4. So the next would be 4, etc. That means 2 plus 4 plus 6 plus 8 plus 10. Let's look at this one. The sum from I equals 1 to n. So we don't know where we're going to stop. That's why there's a generic n up there of 1 over I. Well, we started an I value of 1. So the first term we see is a 1. Then plus an I value of 2. So that'd be 1/2. Plus the next I value is 3. So you'd have a 1/3. Plus a 1/4. Plus, sometimes I just call that yada, yada, yada. I don't know how many terms are in there because I don't know what n is, but I do know I'm stopping at n, which means the last term here is plus 1 over n. And then finally, let's look at this one. The sum I equals 1 to n f of x sub I delta x. So you see where the I is here. It's a subscript notation. So this means f of x sub 1 delta x plus f of x sub 2 delta x, plus f of x sub 3 delta x, plus yada, 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 plus, see, I don't know where I'm going to stop, but I am stopping at n. So the last term is f of x sub n delta x. So like I said, you've probably seen the sigma notation, at least in a college algebra class. I, kind of wanted to review it very quickly. Okay, now let's say we want to approximate the area shown in the figure to the right. So here's the figure, and we want to approximate the area that's under the graph of function f between the vertical lines x equals a and x equals b, and it's above the x-axis. That's the region that is shaded. Now we know there are formulas from geometry that give the area of certain figures, like squares, rectangles, triangles, circles, trapezoids, etc. We're going to focus primarily on the rectangle because the rectangle is very easy to find the area of. We know the area of a rectangle is base times height or length times width. So what we're going to do, this is the game. We're going to look at that interval A to B, and we're going to divide it up into n parts. That will produce what are called subintervals. Now the width of each subinterval, it can be called the step size, and it's just denoted with the delta x. and it's going to dictate the width of a corresponding rectangle. And then when the interval AB is split into n subintervals of equal length, so that means each subinterval has the same length, we have what is called a regular partition. That's just the vocabulary term for it. And the delta x, which would be the base of each rectangle, the width of each rectangle, is nothing more than the length of the interval, b minus a, divided by n. So let's now look at an example. This is an illustrative example on what we're going to do. So let's consider the function x squared plus 1 on the closed interval 0, 2. So there's its graph. That's the graph of x squared plus 1. And my question is, how can we approximate the area of the shaded region? Well, I'm going to begin by taking the interval 0 to 2, and I'm going to split it into 4 subintervals of equal length, so it's a regular partition. We're then going to use rectangles to get the approximation. So to illustrate how I'm going to do this, I'm going to head off to the chalkboard to continue this example. As I do this, pay particular attention to how we find the height of any given rectangle, and then I'm going to mention the difference between inscribed versus circumscribed rectangles. So get this graph written down because I'm heading off to the board. All right, folks, here we are. The function is x squared plus 1 on the interval 0 to 2, and we're going to try to approximate this area that you saw shaded on the slides. And here's how we're going to do it. We're going to use rectangles. I'm going to make 4 rectangles. My interval 0 to 2, I've split it into 4 subintervals, all of equal length, so it's a regular partition. And watch how I'm going to put these 4 rectangles in, and listen carefully what I'm saying. So the first subinterval is 0 to 1/2. I'm going to use the left end point of that subinterval to give me the height of the rectangle. The subinterval 1/2 to 1, I'm going to use the left end point of the subinterval to give me the height of the rectangle. The subinterval 1 to 3/2, I'm going to use the left end point of the subinterval to determine the height of the rectangle. And the fourth subinterval, 3/2 to 2, I'm going to use the left end point of the subinterval to tell me the height of the rectangle. And okay, so I've used the left end point of each subinterval to tell me the height of the rectangle. By the way, these rectangles are said to be inscribed rectangles. That's just like bonus information. But we could find the area of each one of those rectangles and then add those areas together. So we'll be adding up the area of 4 rectangles, and that will give us an approximation to the area that's under the graph of x squared plus 1 above the x-axis from 0 to 2, from x equals 0 to x equals 2. And I think that approximation is going to be an under approximation because look, I'm missing some little pieces here. Okay, so to help organize my work, I'm just going to number these rectangles. Let me call the first one A sub 1, the second one A sub 2, the third one A sub 3, and the fourth one, yeah, that's it, A sub 4. So let's start finding the area of these rectangles. So rectangle 1, it's base times height. The base is 1/2. The height of that rectangle, since I used the left end point of the subinterval to tell me the height of the rectangle, the height of that rectangle is found by simply evaluating the function at the left end point of the subinterval. In other words, that's f of 0. So put 0 in and we get the height to be 1. So rectangle 1 has an area of 1/2. Rectangle 2, its area is base times height. Its base is 1/2. Its height, well, remember I said to find the height of rectangle 2, I was going to use the left. I was using the left endpoint of the subinterval. Well, that gives me the height, so that means I need to evaluate the function at 1/2 to tell me the height of rectangle 2. So I put 1/2 in for x. So 1/2 squared is 1/4. 1/4 plus 1. 1/4 plus 1 is 5/4. So the height of rectangle 2 is 5/4. So the area of rectangle 2 is 5/8. Continuing, rectangle 3, its area is base times height. Its base is 1/2. Its height, well, remember rectangle 3, I said its height was going to be determined by the left end point of this subinterval. Well, the left end point is 1, so its height is found by evaluating the function at 1, and f of 1, well, the f of 1 is 2, so rectangle 3 has an area of 1. And then finally rectangle 4, base times height. The base is 1/2. The height is found by evaluating the function at 3/2. So evaluate the function at 3/2, f of 3/2. So let's see, we put 3/2 in here for x. 3/2 squared is 9/4. 9/4 plus 1, that's 13/4. So rectangle 4 has an area of 13/8. So we add those 4 areas together. And what do we get? 1/2 plus 5/8 plus 1 plus 13/8. Okay, well, let's see if I can do this. 9, 8, 17. I get like 38. Is that right? So I get the area to be 38, which that reduces down to 15/4, or if you prefer as a decimal, that would be 3.75. So that's an approximation to the area under the curve, and it's an under approximation. Use the left endpoints of the left endpoints of each subinterval to tell me the height of the rectangle. So let's come over here. Same deal. I'm going to use rectangles to approximate the area under the curve, except this time I'm going to use the right endpoint of each subinterval to tell me the height of a rectangle. So the subinterval 0 to 1/2, I use the right endpoint to tell me the height. The subinterval 1/2 to 1, I'm going to use the right endpoint to tell me the height. The subinterval 1 to 3/2, I'm going to use the right endpoint to tell me the height. The subinterval 3/2 to 2, I'm going to use the right endpoint of that subinterval to tell me the height. So I have 4 rectangles. I can find the area of each rectangle very easily. We know base times height. I'll add them all together. That will give me an approximation, and it will be an over approximation. You see how I'm picking up just a little bit of extra area there? By the way, these rectangles are called circumscribed rectangles. Okay, I'm going to label these the rectangles just like I did over here, except here I'll call them A sub 5, A sub 6, a sub 7, and a sub 8. So let's find the area of each one of those. So rectangle 5, base times height. The base is 1/2. The height, well, the height was found by the right endpoint. So we need to do f of 1/2 to see what the height is. And we know the f of 1/2 is, well, 1/2 comes in here for x. It's 5/4. So rectangle 5, it has an area of 5/8. Rectangle 6, base times height. The base is 1/2. The height for rectangle 6, well, that's found by evaluating the function at 1. F of 1. And we know f of 1 is 2. So rectangle 6 has an area of 1. Rectangle 7, base times height. The base is 1/2. Rectangle 7, its height is found by evaluating the function at the right endpoint of that subinterval. So f of 3/2, and we know the f of 3/2 is 13/4. So rectangle 7 has an area of 13/8. And finally, rectangle 8. Base times height. We know the base is 1/2. The height is found by evaluating the function at the right endpoint of the subinterval. So that's f of 2. F of 2 is 5. So rectangle 8 has an area of 5/2. So we add these together. A5 plus A6 plus A7 plus A8. Let's see, we get a 5/8 plus a 1 plus a 13/8 plus a 5/2. And let's see, that's 13, 26. Like 46/8, which reduces to 23/4, which is, decimally speaking, 5.75. And we know that's an over approximation, but here's what we know for sure right now. This was an under approximation, this was an over approximation. So we know right now the area is somewhere between 3.75 and 5.75. Okay, I agree. That's maybe not the best approximation. And we're going to get better approximations by putting in more rectangles. You'll hear me say this again when we go back to the slides. So we put in maybe 8 rectangles or 100 rectangles. The more rectangles you put in, you're going to pick up more of that missing area, and you'll start deleting that excess area. It's almost like a squeeze theorem in a way. But that's the process of how we use rectangles to approximate. Left endpoints, which, by the way, when you use left endpoints of a subinterval to tell the height, you are doing what is called a left sum. Over here we use the right endpoints of a subinterval to tell us the height of a rectangle. Because we used right endpoints, this is called a right sum. So hopefully conceptually you understand what's happening here. Time to head back to the slides and see what we're going to do when we start to add in more and more rectangles. All right, folks, to recap what we just did on the board, we said that the area of a rectangle is height times base, and the height was determined by the function. The base, well, that was just the length of a subinterval. And I should point out that I could have used that sigma notation. That looks familiar. That was part D of the very first example we looked at. I could have used the sigma notation here. It would have looked like the sum I equals 1 to 4 f of x sub I delta x. Now we can get better approximations for what I was calling the left sum and better approximations for what I was calling the right sum. And we would get those better approximations by using more rectangles, by putting in 8 rectangles, or 16, or 100, or even 1,000 rectangles. Now, we did it by hand using 4 rectangles, computing the left sum, and the right sum with 4 rectangles. Do you really want to do it by hand for 8 rectangles, 16, 100? No, I don't want to do it by hand. We understand the process. We know what's happening. We know we're finding area of rectangles and just adding them all up. Sounds to me like a good task for a calculator program. At the Blackboard class site, you will find a handout that contains 2 programs for the calculator. One is called the left sum program. The other is called the right sum program. And I say at this time, enter these programs into your calculator, and I'll also walk you through this at this time. So there are the programs. Let me call up my calculator here. It's going to take a while for it to load. And I'm going to just walk you through each one of these. All right, so I'm going to start off by focusing on entering the left sum program. So I come to Program, come over to New. I'm creating a new program. I'm going to call this Left Sum. So I need to find the L, and it's right here. So left sum, hit enter. Okay, prompt A. So remember, prompt, that's a programming command. I believe it's an IO. It is number 2. So I'm going to prompt A. New line, prompt B. So prompt A, that's going to be asking us for the left endpoint of the closed interval. Prompt B is asking us for the right endpoint of the closed interval. And then prompt N, that's going to be the number of subintervals, which matches up with the number of rectangles. And then we're going to do B minus A, put that in parentheses, divided by N. So B minus A divided by N, that's telling us the step size or the base, and that gets stored into alpha D. And then 0, well, 0 gets stored into T. It's the beginning of like a loop here. Okay, 4 is a programming command. There it is, number 4. So 4, I, comma, 0, comma, n minus 1. Oops. N minus 1. And the next line is A plus, okay, now that's I times D. There's no space between the multiplication and the D. I don't know why the typesetting showed that. So a plus I times d, that gets sent to x. And then t plus d times y sub 1. So remember y sub 1, vars, over to y vars function. That gets stored to alpha t. And then end. So let's see, programming end number 7. And then display. That's another programming command. I think it's an IO, yeah. Display. And those are quotes. The quotes didn't, those are quotes right there. Let's see, quotes are right here, hidden above the plus sign. So quotes, and then I have to type in left sum. I'm gonna alpha lock my keyboard here. So left. Then I need a space. This is the space right here. So left sum. Approximation. I'm just going to do approx. And then I need a quote. And I need to get out of alpha lock. Comma. And then alpha t. Okay, so I have the left sum program entered into the calculator. I'm going to go ahead and I'm going to put in the right sum program. So I need to move my calculator so I can see the right sum program. So this is a new program, create new, right sum. So I'm just abbreviating that RT sum. New line. And then prompt. Man, it looks the same as left sum except for maybe one line. Prompt A, then I have prompt B. And then prompt N. And then B minus A divided by N. That gets sent to D. New line. 0. Okay, 0 sent to T. And then 4. Okay, alpha I, comma 1, comma N. That's that one new line, the one different line from the left sum program I was talking about. We have A plus I times D. That gets sent to X. And then T plus D times Y sub 1. That gets sent to T. New line. We're going to end this loop. And then we're going to display quotes. Let me alpha lock. Right sum approx. And there's my space. And then I'm getting out of alpha lock, comma, T. All right, folks, so now I have both I have both programs entered into my calculator. So if you need to pause the video and go back and slow stuff down to get the programs entered into your calculator, please do so at this time, because I'm going to do an example where I am running the programs. So we're going to run the left sum and right sum programs for 100 rectangles for the given function on the indicated interval. So the first function is x cubed on the interval 0 to 2, the closed interval 0 to 2. So let me do that part. Let me get my calculator back up. Okay, so to make the left sum and right sum program work, to make them run, let me clear this. I need to get into y1, the function I'm looking at. Well, the function is x cubed. So now I'm going to run the left sum program. And the first thing it asks for is a. Well, that's the left endpoint of the closed interval. That's 0. Then it asks me, what is b? That's the right endpoint of the closed interval, which is 2. Then it's saying n. What is n? Well, n's the number of rectangles, and it says we're going to do it for 100 rectangles. So I hit enter, and I get the left sum to be 3.9204. All right, now let me run the right sum program. So right sum, same function. So it's the same a, same b, the same number of rectangles. And I have the right sum approximation is 4.0804, which means I can write, at this point in time, I can write a compound inequality. 3.9204 is less than the area, is less than 4.0804. And in a minute I'll go to the chalkboard and I'll put that on the chalkboard. But that's a pretty good approximation for the area. So before I go to the chalkboard, let's look at part B. So part B, see, my function is sine x. So I need to get sine x into y1. And okay, I'm gonna run my left sum program. Notice here a is 0, b is pi over 2. So pi over 2. And, well, 100 rectangles. And here it tells me that the left sum is, I'm just going to round that to 4 decimal places, so 0.9921. And now I need to run my right sum program. So program right sum, going to execute that. A is 0, B is, well, B is pi over 2, still 100 rectangles. And here we get the right sum is 1.0078. So again, I can write a compound inequality that says 0.9921 is less than the area, is less than 1.0078. And let me head off to the chalkboard real quick because I want to write that down on the chalkboard and maybe make a few other comments. So here I go to the chalkboard. All right, folks, in this example, we ran our left sum and right sum programs for 100 rectangles. Happy we have the programs that will do it for us very quickly. For these functions on the intervals, so we ran the programs, we saw what the left sum was and what the right sum was for each. I said I was going to come to the board real quick to tell you how to write this down. You should be able to write a compound inequality. That you know the area Well, the left sum for part A was 3.9204, and the right sum was 4.0804. So you can write a compound inequality that the area is somewhere between 3.9204 and 4.0804. For part B, we ran the program, we saw what the left sum was, we saw what the right sum was. Again, write it as a compound inequality. You know, 0.9921, well, the area is going to be a little bit larger than that, and it's definitely smaller than the 1.0078. So I said I was going to run to the board real quick to show you how to write these down, because this is, you'll hear this at the end. This is how I'm going to change the directions to the exercises I have assigned in this section. I'm going to tell you to ignore the directions. For whatever exercises I assigned, I'm saying run your program for 100 rectangles and then write a concluding compound inequality statement. So let's head back to the slides and see what's next. All right, now for each one of these, of course we could get a better approximation by putting in more rectangles, say 1,000 rectangles. We could run our programs again. And it's kind of nice that these programs are, actually doing the calculations of finding area of rectangles for us very quickly and then adding them all up for us very quickly. That's nice. And also notice that as we add more rectangles, we're kind of in a way employing the squeeze theorem. Continuing on, my programs that I have for you, they use the left endpoint of a subinterval to determine the height of a rectangle, and that was called the left sum program. And then the right endpoint of a subinterval, the right sum program, was used to determine the height of the rectangle. So it used either the left endpoint of a subinterval to give you the height of a rectangle or the right endpoint of a subinterval to determine the height of a rectangle. We can relax that condition and say you don't have to just use the left endpoint or the right endpoint of a subinterval to determine the height of a rectangle. You can use any point in the subinterval to determine the height of a rectangle. It might be kind of difficult for me to write a program to do that, but we can do this. And by doing so, using any point, it gives us the following definition. If your function is continuous and non-negative on the closed interval AB, then the area of the region bounded by the graph of the function, the x-axis, and the lines x equals a and x equals b, well, that area is given by the limit as n goes to infinity, the sum I equals 1 to n, f of c sub I delta x. And here delta x is b minus a over n. So it's saying we're letting the number of rectangles go to infinity. That's the limit as n goes to infinity. Here we have f of c sub I. C sub I is any point that would be in a subinterval. So f of c sub I, remember that's telling us the height of a rectangle. Delta x, that's telling us the base of a rectangle. So when you do f of c sub I times delta x, that's giving you the area of a rectangle. Sigma means add it up. And I have some of that in a note down here. Remember, b minus a over n for delta x, that implies a regular partition. So when n approaches infinity, when the number of rectangles approach infinity, that means the width of any given rectangle, it's approaching 0. In the next section, we're going to relax that condition where we don't have to just use a regular partition. And again, c sub I is any point in the subinterval. So this is a very, very short, sweet introduction to how to approximate area under a curve. And that's all there is to this, this video. You can now do all the homework in section 5.1. I don't have many homework problems for you, but I am going to change the directions for the homework problems. Basically, ignore the directions. I want you to, for the functions given, I want you to run your left sum and right sum program for 100 rectangles and then write a compound inequality like I showed on the board for the example we did. So that's it for section 5.1. Go do the homework in section 5.1. Thanks for watching.